let's carry on. So, as I mentioned, I want to iterate the Morse complex construction. Again, the strong assumption is we are working over the field. So essentially, if an element is non-zero, it is invertible. That's kind of essential over here. And I want to show that if we iterate this construction, what we can get is both homology and persistent homology. Because we are over the field, again, if the incidence coefficient of two cells is non-zero, then thanks to this algebraic version of discrete Morse theory, you can find in the book of Dmitry Kozlov, also a little bit in the book of Nick Scoville, we can do the pairing. And I really want to think about it algorithmically. So I have an algorithm that I can input a chain complex, and it will create a Morse complex of the chain complex. And then I can run the same algorithm again on this Morse complex of the chain complex. So I want to iterate the algorithm with the assumption is that if there is at least one possible pairing that could be done in my chain complex, then the algorithm will do this pairing. So it's not difficult to figure out a algorithm to do it. So an A algorithm may just go through the cells, look if there are any pairs of cells with non-zero incidence coefficient, and do the pairing, and then return the resulting complex. So that's the simplest possible solution, which kind of satisfy this this assumption. So we'll apply the algorithm iteratively, and homotopy type won't be preserved after the first iteration, but when it comes to homology, it preserves the homology. And what we need to realize is that if we start from a finite complex, and at every step of every implementation, every iteration of the algorithm, we are doing at least one pairing, then eventually the stuff will stabilize. I'm claiming that I can read off directly the Betty numbers out of it. Can also get the generators I'm not going to speak about. So, I couldn't start with anything else, but it's on my slides for like 12 or 15 years. I mean, this project which has been in the back burner for quite a while. The downscap. So we are gluing the sides together according to a numeration. So those are glued together this way, and then we need to glue the bottom one with the twist. So that's the optimal. I think you call it optimal, but it's not perfect because, right, so we have one critical cell in dimension 0. This is just the same thing. One critical cell in dimension 1 and one critical cell in dimension 2. And essentially the gradient paths are pretty easy. So let's think that this is a repeller. So it is repelling the vector field to the boundary. And then in the boundary, it's being repelled to the vertex. It's pretty easy to realize that you cannot have a closed V-path, and therefore that is a valid Morse pairing. And if we start to compute the Morse boundary, we need to count the number of paths. So I kind of highlighted them. So a paths going from the boundary of this critical 2 simplex to this edge. There's one over here. There's one over there, and there's one over here. So we have 3 paths. I'm working modulo 2 because I'm lazy. 3 modulo 2 is 1. So this the incidence coefficient of that 2-dimensional simplex and this edge is 1. And if we look at the incidence between the 1-dimensional cell, the 0-dimensional cells, where there are 2 paths, one goes this way and another goes this way, so 2 modulo 2 gives 0. So the incidence coefficient is 0. So after this first iteration, the situation I have can be kind of clumsy way visualized like this. There's one more pairing I can do that cancels out the critical edge with critical 2 simplex. And what I'm left with is a vertex. So after 2 iterations, I got the homology of the downscap, purely kind of by iterating a dummy procedure to compute the discrete Morse complex. Okay. Okay. So I'm claiming that I can do more. Not only homology, but also persistent homology, including pairings, by drawing arrows. So we don't need to do Mandari matrices and such. We'll be just drawing arrows in an appropriate way. And if we draw enough arrows, we'll get persistent homology. That's kind of the claim. So I have a complex. At some point, it will be a chain complex. Some people may call it Lefschetz complex with a filtration function. So you have a standard requirement of the filtration. So if A is a phase of B, then the filtration of A cannot be greater than filtration of B. And I will call a pairing compatible with a filtration if the two cells that are being parted together, they need to have the same filtration value, right? So I'm pairing an A with V of A. I'm pairing two cells. I'm putting an arrow. The pairing is compatible with the filtration if the kind of the beginning and the end of the arrow. So if I am pairing this edge and this triangle, they should have the same filtration value. And if this is the case for every pairing, then I call my pairing compatible with a filtration. So we'll work in the two steps. In the first steps, I'll try to iterate my construction, but my algorithm is only allowed to do pairings which are compatible with the filtration. Okay. And then, if you look at my old paper, show that we actually this way we are preserving persistent homology of the complex. And I won't be presenting a proof. I'll show it to you on the example. So first I will show you a filtration, and then I will show you a dummy way of doing pairings, and we'll try to observe that we are actually preserving the persistent homology. So I'll show you the filtration as it progresses. So in the time 0, we have one connected component. It's in the form of four zero-dimensional simplices and 3 edges. At the time 1, we have another connected component, kind of a mirror image. At the time 2, well, there is no change in homology. At the time 3, this connected component right here dies because it's get merged with a connected component that was born earlier. At the time 4, we have a birth of a one-dimensional homology class. At the time 5, we have a birth of another homology class. So now we have Betty1 equals 2. And in the time 6, both of those homology classes in dimension 1 dies because they are being glued together. So every cell is the number next to every cell is the filtration value, and that's my filtration. So let's think of the the persistence intervals we are getting. So first of all, we are getting this infinite persistence interval. We also have an interval from 1 to 3. So it's there is this connected component created at the time 1, and it's merged to another connected component that was born earlier at the time 3, and therefore it dies at the time 3. Hence this persistence interval. And in dimension 1, we have something that is born at time 4 and dies at time 6. Time 5 and dies at time 6. So this is the birth of the first cycle. There's the birth of the second cycle, and they are both dying at the time 6. Hence those persistence intervals. So right now, I'll take this guy, and I will be doing some pairings. I won't be doing all the possible pairings. I mean, you can do much better. What I want to do is I want to iterate. I want to show you as much as possible on that example the process of iteration in the case where my algorithm is not perfect, right? So I did, the 4 pairings. There are pairings when the tail and the head of the arrow have the same filtration value, so they are compatible with the filtration. I do some more pairings. So you really need to think that right now I am actually working on this iterated on the complex for which that thing is collapsed. This thing is collapsed. I should make a better illustration for this. but you know, I can still do those pairings because they are not affected by the other ones. And there's one more pairing I can do right now. So if you look at the boundary of that cube, that two-dimensional cube, if we follow the gradient path, we can reach either this or that edge. So either this or that edge is in the boundary of that guy, and they have the same filtration value. So I'm kind of denoting this longer pairing, like, you know, with that arrow. And if you look at this and convince yourself that there is no more pairing I can do that are compatible with a filtration, let me highlight for you what is critical right now. So, you know, this guy has something with filtration 4 in the boundary. It has something with the filtration 5 in the boundary. So that's lower. Likewise, you know, over here, we have something with the filtration 5, something with a filtration 3. So if I draw a Hasse diagram, and I name this guy X, Y, this is E, this is D, this is A, this is B. That's the Hasse diagram, and that's the boundary relation that I have. And what you can observe is that, actually we can go through this together. So boundary of Y is C and D. So there is Y, there is C in the boundary, and there is D in the boundary. For X, there is D and E, and so this is X. There is E in the boundary, and there is D in the boundary. And the edges C, the edge C have B in the boundary and A in the boundary. The same for E. So if I'm going this way, it has B in the boundary. If I'm going that way, it has A in the boundary, and there is an edge D. So if I go this way, there is A. And if I go this way, there is B in the boundary. So that's the Hasse diagram. I put the name of the cell and the filtration. And what you notice that if I have a cell, if I look at the boundary has filtration values strictly below the filtration value of the cell. And therefore, I cannot make any other pairings that are compatible with the filtration. And again, if you look carefully at that diagram, so I try to make a, you know, I'm kind of geometric person. I like to think in the terms of those objects. So I try to make a plot which represent this complex. And right now we have this observation, which I mentioned. So if you have an element A and elements in the boundary, then the filtration of A is strictly greater than filtration of every of the boundary elements. And I claim that as a minimal cell complex with the same persistence as C. And if you look carefully at the complex, you can already see the persistence intervals we started from. That's, you know, you can see them directly because that's a simple example. In general, there's still some work that you need to be doing. Now what I'm going to do, conceptually, I'll be looking at the filtration, starting from the lowest possible level. And at every level of the filtration, I will again do the iterated Morse complex construction by pairing cells only at this level or below. And I will do this pairing as much as I can until no more pairings are possible. And when no more pairings are possible, I will move to the next level of filtration and do the same thing. So I'll start at the filtration level 1, do all the possible pairings. Well, at the filtration level 1, we only have those two vertices, no edges, no pairings are possible. So my job is pretty easy. Then I'll move to the filtration level 3. There will be some pairings possible. And I'll take it from there. So let's take a look. So when I'm at the filtration level 3, E, B, and A are already over there. And well, I'm using Elder rule, so I'm always pairing with the youngest element in the boundary. Over there, they have the same filtration, so I can pair with anything. But once I'm doing a pairing of a cells of different filtrations, I need to report a persistence interval, so I'm doing it over here. And when I do this pairing, you remember in the Hasse diagram, I'm actually reversing this arrow, and then those two guys disappear. And if you look at the boundary of D, so I got A from here, but I can also get to A going from D to E to back here. So it cancels out, and very much it also cancels out with C. So A is in the boundary of C, thanks to this arrow, but I can also go here, here, and there. It also cancels out, and therefore my Morse complex after this iteration looks like this. And there is nothing more at the filtration level 3, so there's nothing more I can do. So I'm simply moving to the next filtration value, which in this case is 5. There's not much I can do on the filtration level 4. Then 5, there is not much I can do. So the next non-trivial step is when I'm on the filtration level 6. Come on. And then, there is the elder rule. So I'm pairing a cell with the youngest child. Once again, because I'm doing a pairing between elements of different filtration values, I do need to report the persistence interval, so I'm reporting it. And then again, when I'm doing this pairing in the Hasse diagram, it's equivalent to reverse this arrow. So I can recompute the boundary of 6. I'm going this way. So right now, C is in the boundary of X. And I can do one more pairing, right? There is a non-zero incidence coefficient, so I'm doing this pairing, reporting a persistence interval. And what is missing, the only thing that is left is the vertex A. There is nothing I can do, there's no pairing I can do, so this guy survives as the infinity class. And this way I did recover the persistent homology by simply drawing arrows in an appropriate way. Does that make sense? So what I'm saying, essentially, is everything I told you yesterday about the boundary matrix reduction, you can also do using, at least over Z2, using discrete Morse theory in an appropriate way. An iterative construction of a discrete Morse theory. So there is a connection. If you know Morse theory, you can compute persistence using matrix reduction. So we can do one way. Now I want to do another way. I want to say if you can reduce the matrix, then you have a pretty good recipe on the Morse pairings. I want to show you the other way, all right? Everybody is okay for moving forward? Okay. So right now, imagine that I'm an expert in matrix reduction, and I want to give you your Morse pairings. So there's this concept introduced by Uri Bauer on the apparent pairs. Yes?
This algorithm has the same complexity.
Yeah. Yeah. You can translate one to another. And it's really one-to-one translation. Any other question? Okay. So the apparent pairs. The definition is ugly, as usual, but the concept is very easy once you realize it. So let's take a look together. So we have a complex element-wise filtration. Element-wise filtration means that no two elements have the same filtration. So essentially you have a good ordering, and therefore there is a unique way you can write down your boundary matrix. That's the requirement. And we have a pair of simplices. We call it an apparent pair. So this is sigma I, sigma j is an apparent pair. If sigma I is a maximal phase set of sigma j, and sigma j is a minimal cophase set of sigma I. Sounds Chinese, right? Okay, I'm looking at the pair of a simplex and something in the boundary. And what's the requirement? So the element in the boundary is the last in the filtration. So this is the youngest child, or the youngest boundary element with respect to the filtration, right? So if I have a simplex, and the filtration of the boundary elements are like this, and that's the guy, because it is the youngest one. It is born latest, right? So that's one condition. but there's this other one. So if I'm looking at all the faces that 3 is incident to, then this guy needs to be the youngest. And then and only then, we call it an apparent pair. Why apparent pairs are nice? Well, you can imagine that there will be an arrow, right, between sigma I and sigma j. Let's take a look. So this is an example we've been looking at yesterday. And those are the apparent pair. So remember, maximal phase set, minimal cophase set. Let's take a look. So I'm saying that A, B, and B is an apparent pair. Why is that? Well, because B is a maximal phase, and AB is a maximal cophase. What do I mean by that? Well, there's another element in the boundary of AB, which is A, but it appears earlier in the filtration. It's older. That's why this is an apparent pair. Likewise over here, I mean, because this is the lowest element, C, then A appears earlier, that's okay. But also if we look at other elements in the which are incident to C, so there is AC, there is this BC, and there is CD. And this one is the youngest one. This is older because it has filtration 6. This has filtration 7. This is filtration 8. So AC is the youngest cophase. Therefore, this is an apparent pair. But this guy is not an apparent pair. Why? So if we look at C and BC, well, it's not, because there is a youngest cophase, which is this one. And therefore, BC and C are not apparent pairs. CD and D are apparent pairs. So CD and D, well, if we look at D, it is a boundary of this edge and that edge, and this edge is younger. Therefore, this is an apparent pair, but this is not an apparent pair. And ABC and BC, so ABC is this triangle and BC is this edge. Wait a second, ABC and B. Yeah, so this is the youngest phase. And this is the only cophase, so we don't need to check anything. So those are the apparent pairs. And we can pair them. And it's easy to prove, and actually that there's a simple lemma in Uli's paper. And once we do this will be a gradient field. There will be no loops. And what we are missing is those cells are giving us the infinite classes, right? And moreover, if we look at the pairings, very much like we did during the iterated Morse complex construction, we immediately recover the exactly. Moreover, I mean, over here, this is a very simple example. I can do one step of apparent pairs, construct a discrete Morse complex. There may be some more apparent pairs to be done. So I can, there is also this potential iteration process. I don't know, I'm taking this back, sorry. I'm getting also confused and tired. So this is the way to constructing discrete Morse gradient, if you know how to compute persistent homology or homology using boundary matrix reduction. Okay? Using the apparent pairs. Questions? Okay. Okay, so let's see. Now we have half an hour and we have options. So I can discuss not theory, but this is what I did in Mérida in January. I can take a look and ask a question because we are living in the world of discretization. We are working with discrete objects, while most of the mathematics is dealing with a continuous object. And there is always a question: can we actually prove or approximate, for instance, persistent homology up to a constant, and we can be mathematically sure that the approximation is exact. So we can do some rigorous numerics as you wish, or we can go back to knot theory. We can do some rigorous numerics and then look a little bit on the Conley index and the idea how topology is useful in dynamical systems. Choice is yours. Who wants to go with a knot theory and mapper? Okay, let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, rigorous dynamics. Oh my gosh, you don't make my life easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Mr. Chairman, there is a tie. What should I do? You choose. That's delegation of responsibilities. Once more. One more time. Knot theory. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. Remember 15. Rigorous dynamics. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, guys. Okay, I'll try to be quick. So, Radmila told about it, and many people did. So that's the use of mapper in knot theory. I'll try to squeeze both, all right? It will be like a Scatman style thing when I speak like 3 words per second. So when you're looking at knot theories, they work very much like people in data science. So they have complicated objects to analyze, and well, it's not clear how to do it. Therefore, they attached some invariants to the object. They attach invariants in the way so that if I transform in a nice continuous smooth way, the node I will get the same invariant. Not necessary. So not necessary to different nodes get the same invariant. Wait a second. Say it again, Paweł. So it may happen that 2 different nodes get the same invariant, but one embedding on the same nodes will always get the same invariant. And nodes. This is a very nice playground because there is a lot of them. If you take the minimal crossing numbers of a projection as a complexity measure, the number of nodes is growing exponentially. So you can note that on the y-axis we have exponential scale. And they figure out many knot invariants. And there is a lot of software. I mean, the field is much more developed in TDA. People have been using data science techniques over there, including some of the Nature paper, which is pretty uncommon in mathematics. So DeepMind is also related with this research. What I'm going to speak about is to use the use of knot polynomials. So given a knot, they're trying to build a polynomial, maybe a polynomial of 1 variable like Alexander or Jones, or maybe a 2-variable polynomial like Homfly PT. And I mean, being a Polish guy, I need to mention that there are 2 Polish guys over there, P and T. As you can see, that's Polish. You can actually assign homology theory. Look at the Betty numbers of the homology theory, as Kovanov did. And I mean, you can translate those polynomials if you fix the basis and fix the span of the polynomial. You can translate them to a point cloud. So this is precisely where TDA is useful. What you need to be aware of is the point cloud has integer values. So it's kind of, untypical data for TDA. And if we fix it, then we see that if we are considering nodes up to, I think, 15 crossings, the dimensionality is pretty high. But this is where we can use, for instance, mapper, ball mapper in this case. This is for Jones polynomial data. Jones polynomial of nodes up to 15, 16, and 17 crossing, colored by node signature. That's the stability. So we are looking at the different values of the epsilon, the different values for which I'm constructing the epsilon net. So of course, smaller epsilon, more points. I need more balls to cover it if I have a smaller radius. Larger radius, fewer balls. But we see this amoeba type structure appearing over here. There has been question, and I was trying to motivate why we are doing topological visualization. We are doing it to state hypothesis. In biology, maybe there is something this thing about this group of patients. Maybe they can be helped in another way. We can also ask the questions in pure mathematics. So we've been playing with this. Over here, you can see a ball mapper of an Alexander polynomial, more classical polynomial, and we colored it by a signature. It was an absolute mess. But then we decided to color it by signature modulo 4. Why? Well, because we have a knot theorist in the team, and she told us to do so. And then we got this. It looks like a theorem, right? So what we try to do is to fit a hyperplane that separates those knots which are equal to 0 modulo 4 with the signature equals 0 modulo 4 and those which is equal to modulo 4. We put up a hyperplane and we find the normal vector to a hyperplane. Smells like alternating sum of coefficients, right? The same hyperplane works for Jones. Yes, we start to prove it. It was morning Polish time. Then around lunchtime, Radmila woke up. I haven't spoken to her for like 2 weeks. That was the biggest embarrassment. However, Conway actually have it in his books, but we still haven't found a theorem which is not known yet. We are still chasing. However, you can see that if not for Conway, we would have a nice theorem which we could get out of the this type of the techniques. Another thing, I think it's very important generalize. I'll tell you about. Tell me. I'll tell you about it from a perspective of a data scientist. So if I have a complicated object, knots, I have one characteristic of knots, which is Alexander polynomial, and I have another characteristic, which is a Jones polynomial. Which is better? And of course, I mean, people in knot theory realize that there are knots which have the same Alexander in different Jones. There are knots that have the different Jones and the same Alexander. So in principle, they are not comparable. But what we can do, I mean, we have a nice picture now. We have a ball mapper of that thing. We have a ball mapper over there, and we know which knots are sitting in every cover element. So we can ask, where are the knots from this region of the space of Jones of Alexander polynomial in the space of Jones polynomial? And they are here over there, so they are colored by the red color. So Dave, you asked about the way of coloring stuff. That's exactly this example. And as we move across Alexander, we also move across Jones, but Jones seems to be more discriminative in this dimension. So if you are doing any inference using machine learning, take Jones. That's what you can read out of this. And keep in mind the technique is general. You are looking at nanoporous materials. You have this characteristic and that characteristic, which is better. You can make a similar plots. We have a software for this. You can play with also this type of visualization. And I'm not sure if I want to go with this, but I mean, there are a number of algebraic relations between two-variable polynomial, which is Home-Fly PT, that specialize both to Alexander by this substitution. So we substitute the first variable with 1 and the second variable with square root of t minus 1 over square root of t. And also specialize to Jones with this substitution. Well, it kind of looks like a lens function, right? The only difference is this guy is 30-something dimensional, this guy is 50-something dimensional. But we are getting a cover of our range. You remember in Mapper, when we have this, we took a cover of the range, overlapping cover. Well, we have an overlapping cover over here in the ball mapper of Jones. We have an overlapping cover over there. We can pull it back. We are getting something new. And Radmila, if you are listening to us, I think you could tell more about the stuff that we are having over here. But it kind of makes sense for knot theorists. And I will not, I mean, I know there are knot theorists in the room, so I will not try to make sense out of it because I'm not theorists. But, with this play, you can actually explore the space of possible not invariance, and try to get some insight. So it's not only about the discovery in physics, biology, medicine, but I strongly believe that this techniques can be used in some cases to state a hypothesis in pure mathematics. Very much like the Nature paper on the knot by people from DeepMind. They state a hypothesis. Here's an invariant that do something. Somebody else came and proved it. And the hypothesis was actually almost stated by the AI. And that's yet another way of doing this. So that was a quick, I will try to satisfy both groups. So that was a quick tour on the knot theory. Let me briefly mention to you the rigorous arithmetics. Come on.
I have a question in this work of wall mapper and no?
Uh-huh.
What is that work most difficult computational challenge in this work?
What was the most difficult computational challenge? To gather the data. Gather the data. I mean, John's polynomials over here, Alexander polynomials over there, and they should be indexed in the same way according to the knot atlas. They were not. So data curation over there was a big challenge. Except from this, I mean, some questions came up naturally, and they lead into development of new algorithms, which I briefly highlighted over here. So the computations by themselves, they were not challenging. Trying to gather different data sets, which, if you use SQL language, they don't have the same indexing thing. So you cannot make a join properly. And making a join properly, that was a challenge. But it was a dirty work, if you wish. It wasn't a mathematical work. Once we have the right data, it was it, and you can essentially, there was a GitHub repository. So if you go to the Oscuri GitHub, not theory, you can actually redo these computations. So the data are not on GitHub, they are in Zanado, but the data you can also download, and you can do it on your laptop. So it's not a heavy lifting stuff, if that's what you mean. Okay? Any other questions? Yes?
You mentioned about classifying the mapper work, not classifying exactly, but giving that kind of ideas from the visualization
Uh-huh.
In polynomial environment.
Uh-huh.
But using another kind of environment like group environment or
So you're asking me to make a TDA type invariant of a group. Let's work on this. I don't know how to do it. Yeah, I mean that's a very relevant research question. The answer is I do not know. Yes. I'm not the right person to ask. We can ask Radmila. I mean, we did not. So for some reasons, she did not, but I don't know the reason why. That's the best answer I can give you. Okay. Any other questions? Oh, sorry, guys, almost forget. Okay. So, rigorous computations on the computer. Who is actually following Starship and the SpaceX thing? 1, 2, 3. Okay, 4, 5. I mean, what's fascinating is when they are firing the rocket, they if you are sailing on Mexican Gulf Bay, you shouldn't be going to certain places because this is where the rocket may fall if something goes wrong. And the idea I'm going to speak about, the rigorous arithmetics, goes back to the early days of US missile tests. So it goes to the days of 70s, when they were trying to predict, okay, if the rocket goes out of trajectory, can we provide a raw estimate of the region in which it can fall? in the way that if it falls, it will fall over there and not in some other region. So we just mark it as restricted region. Nobody will be over there and nobody will be had. Obviously, you cannot do it with finite precision arithmetic because the errors are accumulating as you are doing computations. And the more idea was to represent numbers not as, some digits of precision, but as intervals. The intervals that the endpoints of the intervals are representable number, and we can do the arithmetic computations in the way that to ensure, I think I have it on the next slide, in the way to ensure that the results of the computation, whatever true result is, so if I take any x in between a and b and any y between c and d, then the result should be over there. And I'm making sure that this is a representable number and that's a representable number. It's not that difficult to actually compute it, because so here's a hardware thing in the computers. When you are working on floating point arithmetic, internally your processor is using more digits of precision, and it actually reports back to your RAM memory. And what you can do, so what we did back then, it was like 15 years ago, you can go to the assembler, which is the lowest level programming language, and you can ask the computer, so for instance, what do I need to do over here? I have A and C, and I want to add them. In ideal work, I just say A plus C. It may happen that A plus C is not representable in the computer. So in this case, what I want to have is to have a lowest representable, the largest representable number that is just before A plus C. So A plus, my processor will know because it has more digits of precision, and I'm just asking it. So if those are representable numbers, and A plus C lands somewhere here, and I want the end of my interval to be over here. This way, I make sure, and whatever is the real result of this addition, I enclose it from that side and symmetrically from the other side. So when I'm having B plus D ends up somewhere here, then I want this number. And this way, I can do the addition in the way that whatever is the true results of the addition, it is enclosed. Subtraction, multiplication, division, similar, a bit more complicated, but the idea is very much similar. So we can have arithmetic operations on the intervals in a rigorous mathematical way. Can represent functions in a rigorous mathematical way. Taylor series, estimation from above on the remainder of the Taylor series. And then we have multiplication, division, additions, and the Taylor series, approximation from above on the remaining, whatever remaining you want to use. We can make right now, once we have this machinery, which is not that difficult, think about it, we can make rigorous statements. So if we have a function given by some formula which we input to the computer, and we compute the value of the function at point A, and the whole interval is kind of below 0. At point B is above 0. We know that the function is continuous. Using the Darboux property, we know that there is at least 1 0 in between. So we already can prove a theorem using an interval arithmetic. And that's typically what people are doing. So if we have a domain which is kind of in the intervals, we can compute an image and find the largest enclosure of the image in the way that if we actually report this bluish or reddish or whatever the color is region, we are sure that the value of that rectangle, that interval, two-dimensional interval, is inside. So this is how interval arithmetic works. And so let's see, I'll start from the end because I'm not sure if I'll have time. And then if I have time, I'll come back. So imagine that we have a setup. We have a function. So on some domain D, which is the subset of Rn. We have a function from D to R. And can we compute persistent homology of D with the function f on the top of it? So we are really looking at the sublevel sets of f restricted to D, and we want to do the pairings, very much like in the standard persistence. And I want it to be accurate up to a given precision. So you are giving me a function, and say, Paweł, I want the persistent homology of this function accurate with respect within the range of 0.25. Okay. That's a stability result in persistent homology. So what I'm going to do is I will have my D. I will define another function, f prime, which will be not farther away than epsilon from f. And I will guarantee this using interval arithmetic. But this f prime will be kind of defined on some finite approximation of D. If I am able to find such an approximation, finite approximation f prime of f, having the property that the L infinity distance between those two functions is bounded by this epsilon, then what is left is I have a finite complex with a filtration. I run the standard persistence algorithm. I got the answer. So here's my D. What I can do is I can compute using interval arithmetic the value, I call it range over here, of the value of f on the whole thing. Now I simply look at the diameter. So if the value of f will be some interval from a to b, and then if b minus a is smaller than epsilon, I'm done. Because then I can just say, okay, this whole cube gets the value of a plus b over 2. And if it gets the value of a plus b over 2, I won't be farther away than epsilon, because so let's say if b minus a is actually sufficient to say greater, less or equal than 2 epsilon, then a plus b over 2 take it back, is less or equal than epsilon. And if I take the midpoint, well, I will not be making an error greater than epsilon if I approximate it. So if that's the case, I'm done. If not, I'm subdividing this thing and checking on every intermediate one. So let's assume that actually, for those 3 cubes, it turns out that the diameter, indeed there's 2 epsilon. I'm simply tired. Is less or equal than 2 epsilon, then we simply put the midpoint, so the average value, and then we subdivide the place where it actually didn't check up. And we recursively do it if at the end of the day we checked all the cells. We have this hierarchical CW complex, regular CW complex, with a filtration on the top of it. Well, nothing prevents us to input it to either matrix reduction algorithm or to draw arrows using our discrete Morse theory stuff and compute persistent homology of that thing. All those numbers are representable. We are not making any arithmetic operations per se. We are working on Z2 coefficients. So there is no room for round of errors when we are entering the persistent homology world. So we can get exactly the persistent homology of a function provided every cell checks out. So this is how I can actually make this approximation of a persistent homology of a continuous function under the assumption that I can write it down on a computer, and the validation goes through. If it doesn't go through, well, of course you can find a function which is complicated enough, or maybe have infinitely many persistence intervals. Then this validation will simply not go through, and the algorithm will tell you don't know. So in computer science we call it a partial algorithm. So it gives you an answer, then we have a mathematical certification that the answer is correct. very much like a mathematical proof, but it may not give you an answer, in which case you don't know anything. So this is how we can approximate persistent homology over continuous functions using interval arithmetic. Does that make sense? Any questions? Tell me.
It can be used to reduce the number of levels of operations in a
Okay. I don't know. So I can show you one of the examples. It's coming for phase separation. So this is a phenomenon in material science, and we solve it using a spectral method. So you know one thing. So it is a partial differential equation. So we don't have a good way of controlling the errors. But assuming that our spectral approximation, spectral solution is correct, we are actually able to get persistent homology of trigonometric polynomials, quite long trigonometric polynomials, accurately within this technique. So really the setup is, you write down in your Python code very complicated function, and you are asking me, okay, on this domain, what is the persistent homology of that function? So it's not keep in mind, the input is not as standard as in the data science. The input is really a mathematical function. Okay. Okay, so let me just briefly mention. So the other thing I won't have time to speak about is, maybe over here. So we want to approximate sublevel sets of functions up to homotopy type. You can also use a combination of interval arithmetic and automatic differentiation. You'll also get a partial algorithm, which if it returns true, then it will give you an approximation of your sublevel set of your function, which is rigorous, mathematically rigorous. It's not numerical guess. It is a rigorous statement, very much like a proof. It requires some more techniques. Again, automatic differentiation is one of them. Very cool idea of computing derivatives of functions in automatic and rigorous way without approximation errors. So I think there are 3 minutes more. There's absolutely no sense for me to go into the details because I will kill you. And you already look tired, and I'm also tired. So let's stop over here. Do you have any questions? Tell me.
We have all these techniques to take information.
Mm-hmm.
We present it.
Mm-hmm.
And we get a little bit more information about the
Mm-hmm.
case.
Mm-hmm.
And usually we use real world things.
Mm-hmm.
But like mathematics also brings information that
Mm-hmm.
you have theorems and how you can prove one. The path that you can draw with group. Just maybe way of getting to know that one that to my community probably get a number of I think there is more way of tracking of the life. And I think it is possible to start okay for my life.
So guys, we are looking at very complicated logical system of implications. So we have some two theorems that both implies another theorem, and they are decorated by Gödel number. I don't know what a Gödel number is, but it's then the question is, can you do TDA on it? I mean, in principle, yes, if you can interpret it, sure. I don't know enough about formal logic in order to tell you off the spot if the interpretation may or may not make sense, but the question seems to make sense to me. The question for the answer to the question you didn't ask, but I presume that was the question. Yeah. So, many people already thought about it. So what you're driving at is and find for theorems that you can prove to fill in the holes in the knowledge. Look for TDA holes in the knowledge. You'll find something on Google. People thought about it. I don't think they have enough codification of mathematics to actually make it serious. But those ideas were flying around for many years. All right, but holes in knowledge. Google it. All right. Okay.
The data set has to accomplish certain hypotheses to apply these methods and algorithms.
So you're asking if we have some assertions to check?
Yeah.
No. I mean, the results may make no sense, but a priori there are no assumptions. So we don't need to. Sometimes you need to check if the matrix is non-singular. We don't have anything like that. Okay. The golden ratio to division. Okay, so I'll need to go through the whole thing. The other option was the binary subdivision, but because of it, I mean the line, the nodal line as we call it, so the line of the sublevel set. If it crosses the vertex, then we cannot validate the cell, and therefore we randomized it. And the golden ratio normalization actually solves a lot of problem in this material science example. But in order to understand why we need to normalize that, we need to go through an algorithm that would take another 20 minutes. So, it's, kind of normalization in order to make sure that the nodal lines are inside the cubes and not in the boundaries, because that was problematic. Okay. Anybody else?
Not exactly a question.
Yeah, you owned one.
I would say thank you. I saw the problem
Yeah, thank you. I can feel it on my back. Yeah, thank you for staying over, both for those online and especially for you. It was great, and I hope you like the Swiss, and I hope you like even more the lectures. So if you have any questions, and at some point you drop me a line, I'll try to answer as soon as possible. And let's keep the discussion going. I mean, you have very nice initiatives over here with the Geotop. Also, Carlos is putting a lot of effort for interconnections. Let's keep the communication channels open. And some of us are already thinking about some ideas, some projects. Let's keep on discussing it. And about the logic, minimal number of points. I don't know, Rayleigh-Bernard convection stuff. Let's keep in touch. Great to meet you guys, and let's have fun this afternoon. All right. Thank you.